In this video, we're going to explore exponential functions and logarithmic functions. Let's get to it. The general form of an exponential function is as follows. They look kind of like power functions, but the key difference here is that the input variable is in the exponent rather than in the base. The term exponential growth is thrown around a lot in everyday conversation, but this is what it means mathematically. Not only does the function increase with time, but the rate at which it increases also increases with time. A classic use case of exponential functions is in the investing world. Suppose you invest $100 at the start of the year and get a 10% return at the end of the year. By the end of your first year, you'll have the $100 you started with plus 10% of that $100, which is 10. Adding together gives us a return of $110. But in the second year, we start with $110. By the end of the second year, we'll actually end up with $121. In the first year, we earned $10, and in the second year, we earned $11. This is what exponential growth looks like. The rate at which we are increasing also increases. This example can be modeled by the exponential function as follows. You multiply the initial value with a multiplier and then raise that multiplier to the power of x. In this case, we're getting a 10% return, which is equivalent to a 1.1x multiple. If we want to know how much money we've earned after 10 years, then we substitute the value x equals 10 into the equation. And if we do that, we'll see that we end up with $259 by the end of our 10th year. Okay, let's get this one out of the way. Technically, it's pronounced Euler's number, but if you want to call it Euler's number, or even just refer to it as E, that's totally fine. Most of the time, you'll be working with exponentials that have Euler's number as a base. Its definition isn't really important right now, but it does have applications in calculus, which we'll cover much later. One of the ways we can solve exponential functions is to equate their terms. If two exponential functions are equal, it means they must have the same base and the same exponent. Let's look at the following example. First, we should ensure that the bases are equivalent, which we do as follows. Now all that's left is to equate the exponents. After a bit of rearranging, we find that x must equal 2. The general form of a logarithm is as follows. Any exponential can be converted into an equivalent logarithm, and we do this by switching up the terms as you can see below. Remember earlier when I said that most exponentials use a base of e? VCE questions love to convert between exponentials and logarithms, so most of the time you'll find that your logarithm also has a base of e. This kind of logarithm is called the natural logarithm and can be expressed in the following two ways. Another thing that comes up fairly often are the Logarithm Laws. Let's have a look. These are used all the time when it comes to simplifying logarithms. Let's go through them rapid fire. All of these logarithm laws only apply if the base of each logarithm are the same. Let's start with the product law. The product law states that if you have two logarithms of the same base added together, then you can replace that equation with a single logarithm that has the product of both inputs. Now for the quotient law. If you have two logarithms of the same base that subtract from each other, you can replace it with a single logarithm that has the division of those two inputs. Notice that the order here matters. Finally, we have the power law. If the input to a logarithm is raised to a power, you can instead bring that power out the front and express it as an equivalent logarithm as follows. Here's an example where we use all the identities to simplify the equation. We start with the product law, then we apply the quotient law. And after a bit of simplification, we can use the power law to rewrite the logarithm as follows. There are a few more tricks we can use to simplify logarithms. Let's run through them. Firstly, if the input and base of a logarithm are identical, then the output is 1. This quickly becomes apparent when you convert to the exponential form. Secondly, if the input to the logarithm is 1, then we know the result must be 0. And we can see this again once we convert to the exponential form. Finally, if the input to the logarithm is a negative or 0, then we consider it invalid. In the case of 0, it's because once you convert to exponential form, you find that there is no valid exponent that actually gives a result of 0. If your logarithm has a negative input, technically this is valid, but it is outside the scope of math methods. If your logarithm has a negative input, it generates a complex number. And complex numbers are only assessed in VCE specialist math, so we don't have to worry about this here. Let's try an example. One of the questions you'll often be asked in your exam is to find the maximal domain of a logarithm. This means we need to find all the possible inputs that the logarithm is defined for. The third and fourth identities tell us that the logarithm is only valid if its input is greater than 0. Thus, in order to solve for the maximal domain, we need to solve the inequality such that the input is greater than 0. Let's try this example. We start by setting up the inequality. We now need to solve the quadratic. This can be done using two main methods. You can either use factorization and the null factor law, or you can use the quadratic equation. I would recommend using the null factor law approach because it becomes much easier to figure out the inequalities, as you'll see as we go through the example. After we factorize the quadratic, we need to be careful. This expression will only be positive if either one of the following conditions are correct. Either both terms are positive or both terms are negative. This is based around the rules of multiplying negative numbers. If we multiply a negative by a negative, we get a positive. And if we multiply a positive by a positive, we also get a positive. So let's look at each term individually. X plus 1 is greater than 0 if x is greater than negative 1. And it is less than 0 if x is less than negative 1. We can say the same thing for x plus 2, but for the result negative 2. Here comes the tricky part. We need to combine the valid domains. So firstly, we're going to look at the case where both inputs are positive. The intersection of these two domains is x is greater than negative 1, which we can see on the number line. See how they overlap for x is greater than negative 1? We can do the same thing with the negative pair to achieve x is less than negative 2. Now we just need to express the union of these two domains, which we do as follows. Try plot this function on the CAS and see what you get. Remember how we can express exponentials as logarithms? We can actually use this property to solve exponential equations. Let's have a look. Suppose we are told to solve the following equation for x. One thing we can do is take the natural logarithm of both sides of this equation. And using our logarithm laws, we can begin to simplify this. Using the product rule, we can separate the left-hand side logarithm into two separate logarithms. Now, using the power rule, we can bring the x out the front. This leaves that logarithm with an identical base and input, which we know from our log identities equals 1. From here, we'll just rearrange for x and then use the quotient rule to simplify the logarithm to get our final result. If you found this video helpful and would like to see more, I actually have a Google Drive with written versions of these lectures covering the entire Year 12 Math Methods syllabus. I've made these resources available for free on my website. Just click the link in the description below and it'll take you to my website. Just scroll down a little and click this heading to get access. No opt-in required, free of charge.